Hello. So I've got another example for you. Let's get started just reading it. Harry Potter, the guinea pig, is riding a skateboard down the street with a constant acceleration of 0.08 meters per second squared. He reaches a speed of 1.9 meters per second by the time he gets to the end of the street. He started with a speed of 0.3 meters per second at the beginning of his ride because Elwyn gave him a little push. If the end of the street is at 25 meters in the x position, at what position did he start his ride? All right, so we've got a lot of information. First thing you want to do is start visualizing. You got your little mental video of what's happening. You can even start drawing at this point the different aspects of that video that's happening. So if I've got my Harry Potter, I'm going to have him going to the right. So I've got Harry Potter here. There he is. And he's on. Oh, yeah, he's very hairy. That's right. Make sure we get his hair in there. There he is. He's on his skateboard. And he is riding it down the street. So he's going that way. And the street is here. Then we're going to have some locations of interest. This is a pretty basic problem, which means we have one initial location of interest and one final location of interest. When we read the problem, we can see the initial location of interest is when he starts his ride, and the final location of interest would be at the end of the street. We're given information about those specific positions and in space, which corresponded to time, so that we're not given any time information. So we go back, and I've got my picture. I see that Harry Potter starts here. I know that I'm visualizing him riding down the street. At some point, I reach the end of the street. Let's call that the end of the street. And I know Elwyn gave him a little push. That's like, so he had some initial speed to start with. If she hadn't pushed him, or he hadn't pushed himself with his little foot on the ground, pushing himself along, then his initial speed would have been 0. So why is he accelerating? Well, the street has some small, it's a little hill. It's like a tiny little hill. So he's got just a little bit of gaining of speed as he goes down the street. So that's what I see in my mind is what's happening. Now I want to start putting these numbers into my picture. And to put these numbers into my picture, it's probably a good idea to go ahead and categorize our problem at this point. It's going to help us realize which numbers, it's all important, but at some point you're aligning those numbers with equation value variables in equations. And if you already know which equations you're thinking of, it just helps you pick out the numbers you need to some extent. So numbers that are important here, important information. Let's get down here so we can see it. We've got riding down the street with a constant acceleration. And then there's the constant acceleration. And then it goes on. So right there, before I even go further, I probably can classify my problem, because at this point in the class, the only time we've seen constant acceleration would correspond to a 1D constant acceleration problem. As we move on in the class, there'll be other times where something can undergo a constant acceleration, and you might categorize it as a different problem for solution purposes. But right now, that's the only thing we know. So that makes it pretty straightforward. Oh, okay, so if Harry Potter's traveling at a constant acceleration, then this is a constant acceleration problem. And since the only kind we've ever done is in one dimension, we're gonna work it out in one dimension only. And when I look at my picture, I can see that one dimension works well with this picture that I've had in my head anyway. It's just riding along that street, which naturally just draws a straight line. So from here, I can think, okay, constant acceleration problem, I have 3 equations that I'm going to be referencing, right? And I can even write those down right here, or if you have your equation sheet, you can just be looking at them. But V final, let's give this the x direction, and we'll put it in meters. So V final x equals V initial x plus AX delta t. There's also x final equals x initial plus V naught delta t plus 1/2 AX delta t squared. And V final x squared equals V initial x squared plus 2AX delta x. So we have both of those. I mean, not both, all 3 of those equations that we're referencing as we work through this problem. Which one are we going to use, or you may use more than one as well. You don't always have to just use one. Okay, so now I'm going to start going through. So now I started to have like a list of variables that I know I'm going to be trying to fill in. So as I go through my problem, I can start writing down the numbers that are given to me and which variables they're associated with. So constant acceleration of 0.08 meters per second squared, I can just write that down. Okay, that's going to be my AX. And I've got them going to the right. I'm going to have right where it is positive, so then this is going to be a positive number. 0.080 meters per second squared is my acceleration. And now I'm going to keep reading. I have that he reaches a speed of 1.9 meters per second by the time he reaches the end of the street. So this speed happens at the end of the street. It's a constant acceleration that's non-zero, so his speed is changing, and that one is only here at the end of the street. It's not happening any other place, so that would be right here, V, and so that's going to be my final, because right here at the end, this is my final location. Everything that happens with the subscript final is happening in this position, and everything that happens with a subscript initial is at this location at the beginning. So V final equals 1.9 meters per second. And I can put that here as just a list. Next, I've got that he started with a speed of 0.30 meters per second because Elowen gave him a little push. It's this one, speed of, that's your initial. So that's going to be over here. This little arrow that I put in is V naught. Oh, these are all in the X. Equals 0.30 meters per second. And then the next thing in my word problem that's numeric given is that the end of the street is at 25 meters. So this is the end of the street, and it's a location in this reference frame. So that's going to be my X final, because that's my final position there, 25 meters. As I'm looking up here, I can see there are variables we don't know. X final equals 25 meters. Now, we weren't told that he traveled 25 meters. That would have been a delta x. Delta x would be from here to there. What we're told is that this location in a reference frame that's given to me already is 25 meters, which means I don't know how far he traveled. And in fact, what I'm asked to find is what position did he start his ride, which would be his x initial. So we're looking for x initial. That's what we want to find. So So I write it down with question mark. That's what we're looking for. And now we can look at our list of equations and start to think, what do we know? What are we looking for? What don't we know? So I'm going to say I'm looking for, put it in red, I'm looking for x initial. So every time I see an x initial, oh, I put x naught. I'm using knots, so up here in my equation. So I should use a knot down there. All right, so I'm looking for x initial. So this equation, the first equation, it doesn't have x at all in it. The second equation has an x initial right there. And the third equation doesn't have an x initial in it, right? But what it has is a delta x. And inside the delta x is x final minus x initial. So this includes an x initial, which is important to recognize. But it also has x final in it. So I might want to, bearing that in mind, now that I've written everything down, get rid of that and say, you know, I'm going to replace this with x final minus x initial, just so that I can clearly indicate which thing I know and which thing I'm looking for. So I'm looking for x naught. I do know x final, so I'm going to underline what I know in blue. I know x final, and I know x final, and there are no x's here. And I know acceleration, so I'm going to underline all the accelerations. Oh, and you know, I missed putting down on my list. I have my v initial. I didn't get it in this list here, so I want to put it right here. V initial x. I know that as well. So when I look up here, I've got v initial, I've got v initial, I've got v initial. And then v final x, I know it, so I'm going to go up here and underline those in blue. There's no final here, but there's a final there. All right, what don't I know? I don't know time information. I have no time information. So, oh, I kind of skipped this top one here when I did my acceleration because I already know I'm not going to use it, but I don't know that. I don't know that, but this one has no time in it. So you're starting to see now which equation I need to use to solve this, because I'm looking for, ideally, the one equation that the only unknown is the variable I'm looking to solve. So that would be the third one here. So this third one, I know everything except for the initial position, which is what I'm looking to solve. So I'm going to then write that one down. And now I'm going to start filling in the numbers. 1.9 meters per second squared equals 0.30 meters per second, all of that squared, plus 2 times my acceleration, 0.080 meters per second, and that is the second alone is squared in the denominator. And then x final is 25 meters, and x initial is what I'm looking for. Okay, and now I'm going to start solving this, and from here on out it's really just algebra, although keeping track of my units, etc., is really important. So 1.9 squared, use my calculator, I'm going to get 3.6 meters squared per second squared. I'm keeping sig figs to 2. And then 0.3 squared will be 0.09 meters squared per second squared. And I should keep a 0 there, so I have my sig figs to 2. And then 2 times 0.080, I'll leave it like that, is plus 0.16 meters per second squared. And then that is times 25 meters minus like that. Now I'm going to try to get my x naught alone. So the first thing I want to do is get this whole term alone on one side. So I need to get this 0.090 over to the other side. So I'm going to have 3.6 meters per second squared, meters squared per second squared, minus 0.090 meters squared per second squared equals 0.16 meters per second squared times 25 meters minus x naught. And I need to do this calculation. So 3.6 minus 0.090 is 3.51, but see, my least known decimal, my least significant accurate decimal is the tenths place. So I'm going to go 3.5. And my units, they both have the same units as they should if you're adding or subtracting them. Meters squared per second squared equals 0.16 meters per second squared, 25 meters minus x naught. All right, now continue working that down. What I need to do is get this parenthesis alone. You can either distribute this through and then pull that over and then divide, or I'm just going to divide out the 16 over to the other side and then be left with these two terms on this side. So I'm going to take and divide both sides here by 0.16 meters per second squared. Like that. That'll cancel it out of the right side, and I'll be left with that calculation there on the left side. So 3.5 divided by 0.16, that is 21.9. We want to round it to 2 sig figs, so it would be 22 meters squared per... hold on. So we have is meters squared per second squared divided by meters per second squared. So I'm going to go ahead and do this out kind of long. Meters squared per second squared. When I divide, so I've got this in the numerator is this fraction, and then in the denominator I've got meters per second squared. So a fraction, if you're dividing by a fraction, that's the same as multiplying by the inverse, second squared per meter. And I can see that my second squareds cancel out, and this meter in the denominator is going to cancel with one of the 2 meters in the numerator, and I'm left with just a meter alone up there. So what I have is equals 25 meters minus x naught. I have just 22 meters over here. 22 meters equals 25 meters minus x naught. So that's going to give me minus 25 meters, minus 25 meters, and I have minus x naught equals negative 3 meters, and then divide both sides by negative 1, and I get x naught equals 3 meters. Oh, I need to keep my second significant figure, 3.0 meters. 3.0 meters there. All right, so I'll write that nicer. X naught equals 3.0 meters. All right, so this is the location, the component of your position. if I want to write it as a vector x, the initial position x naught would then be 3.0 meters x hat. Where if I think of this, x naught, the vector, is this magnitude x hat. All right. So that means if I go back up here, I got 3 meters is my initial location in this reference frame. So this part right here, I now know that x naught equals 3.0 meters. That was my initial position. So my delta x was 22 meters. X hat, so positive, went from the initial to the final, but I wasn't asked for that. And that is this problem. So it's a pretty basic problem, and we went through it very detailed, but it's a nice example of a 1D constant acceleration. And I wanted to show you one where you're solving for something inside the delta, where you actually know one of the two sides of the delta, and you aren't assuming the other one is just 0. So a lot of times we'll solve for the final time and assume the initial is 0, because we have the ability to just set that initial time as 0 within the problem. In this one, though, because we were told the final time and the final position, and the initial position is unknown, we can't just assume that in this reference frame Harry Potter started at 0. We have to calculate where Harry Potter started in this reference frame, and we find that it wasn't 0. Of course, we could have solved it and found that it was 0. If the x final had been 22, then what we would have solved for in the end, if everything else was the same, the initial position would have been 0, because the delta was 22. So if his final position was 22, then he must have started at 0. But in this case, we couldn't assume, so we had to solve. So it's good practice to see one like that, so you don't get into the habit of just always thinking all the initials are 0. And so you have to read your problem carefully and realize when you can assume that, because you're creating the reference frame initial position, or in this case, the reference frame is defined for us here. And so since they didn't state that his initial position was at 0 and his final position was here, we just know his final position is here, then we can't assume the initial position is 0. All right, well, see you next time.